Okay, this is section 6.3, page 1, and we're going to start off with a theorem that says if a line is drawn through the center of a circle, so here's our line going through the center of the circle, perpendicular to a chord, so it's perpendicular to this chord, let's go ahead and mark that, then what can we say? Then the line, this line, bisects the chord, so we'd be able to say that that is bisected, and its arc. So here too. Okay, let's go ahead and write it down. It says if L passes through the center, okay, and it's also perpendicular, and L is perpendicular to the chord CD, then what can we conclude? We conclude that it bisects that chord, so CB is congruent to BD, those two pieces, and it also bisects the arc, so CE is congruent to ED. Those arcs are congruent. Okay? All right, let's use this information to do this problem. So we're told that OC is equal to 8. So OC here is equal to 8. OE here, that's here, is equal to 6. Okay? And then we know that OE is perpendicular to CD. Okay? And it's all in this circle. Okay, well, what can we say from here? We're trying to find CD. So we're trying to find the length of this whole chord. Well, what do we know? We know from the theorem above that if this is perpendicular, then that means it bisects that chord. So if we can find this piece, we know that it's equal to this piece, and we can add the two together. So how would we go about finding this piece here? We'll take note that that's a triangle. And not only that, a special kind of triangle, a right triangle. So to find the third side, we can use the Pythagorean theorem. So let's go ahead and say triangle OCE is a right triangle. So we're going to use the Pythagorean theorem, which says that a squared plus b squared equals c squared. Okay? All right. Now, which side is which? Well, the one across from the right angle is c, so we want to put 8 in for c. B could be either one of these. Let's go ahead and just put a 6 in there, and we'll solve for a squared. So we get that a squared plus 36 equals 64. Then we'll subtract 36 from both sides, and we get that a squared equals 28. So to solve for a, we have to take the square root of both sides, remembering to put in that plus and minus. Over here, square root of a squared gives us a, and over here we get plus and minus the square root of 28. Let's get rid of the minus. We know that since we're talking about the side of a triangle, it's got to be positive. So let's just say square root of 28. Okay, so now to answer the question, let's go on one step further here. Those of you who know how to do this, you know that the square root of 28, there's a perfect square in there, 4. So we can separate it like this and say that the square root of 28 is equal to the square root of 4 and the square root of 7. And then we know that the square root of 4 is 2. All right? So for those of you who know a little bit about radicals, keep going. If you don't, that's fine. Stop there. Okay, so now we can answer the question of what CE is. CE is equal to either the square root of 28 or 2 square root 7. Okay, well, that's gotten us here. But now what do we know? So let's use, use black here. So we know that this side right here is equal to 2 square root 7. And we know then that means that this side has to be 2 square root 7. So all we do is add the 2 up together, and we've got the final answer. So we know that CD, so we're going to start by saying by the segment addition postulate, we can say that CD is equal to CE plus ED. Add those two pieces together. Now, we also know that this is equal to ED is also equal to CE. And how do we know that? We know that because of the theorem above. By theorem 6.3.1, since OE is perpendicular to CD, it, we'll say since it's perpendicular, instead of it's saying it. How about OE bisects CD? Okay, so that means that those two are the same. Okay, so we have 2 times CE. Well, we know what CE is. It's either going to be 2 times the square root of 28, if we put that in, or it's going to be 2 times 2 square root of 7, which is 4 square root of 7. So depending on the way you're doing it, that's the answer we're looking for, one of those. Okay, so let's take a look at the next theorem. It says if a line through the center of a circle, so if a line through the center of the circle bisects a chord, let's call this line L, bisects a chord other than a diameter, so it bisects this chord here, and it's not a diameter, we can see that, it doesn't go through the center, then it is perpendicular to the chord. All right, so let's try to write that. If L passes through the center, and what else? And bisects the chord, so and L bisects this chord RS, then what can we say? We can say that L is perpendicular to the chord RS. All right, so you may be wondering, why can't it be the diameter? Well, let's take a look at a picture. So why can't the chord be a diameter? Okay, so let's draw a picture here. Here's our circle. Here's our center. Let's draw our diameter. Okay, so there's our diameter. Okay, now let's come up with a line, okay, that passes through the center. Okay, it's going to pass through the center, and it's going to bisect. Okay, so that's our line. Okay, so take a look. It passes through the center. It bisects the chord, but is it perpendicular to the chord? No. So the line passes through center and bisects the chord, but is not perpendicular to the chord. So hopefully you can see, anytime you draw a line through the center and it crosses a diameter, it's of course going to cut it in half because it goes through the center, but that doesn't mean it's perpendicular. Okay? All right, so this example is going to be pretty difficult to do without you being in class and able to ask questions. So we're just going to skip this. Don't worry about that problem. That ends page 1. Go on to page 2.